Hi, and welcome to part 2 in our video series about GaugeR&R analysis. So I've started on the slide that we ended with last time. We have the variance in total is equal to the variance of the measurement system analysis. This can be broken down into the measurement due to the tool itself and the measurement due to the operator, but the measurement of the variance of the measurement system plus the variance of the part. So how we ended before was that we looked at the variance of the gauge was 8%, approximately 8% of the variance of the total system. And so that probably was pretty good depending on what we're looking at. I use the example of frozen yogurt or gold or mixing drugs or something like that. But now what if we have specification limits or user specifications set on it? So that's a term similar in concept to our process capability when we're talking about control charts, but this is the precision tolerance ratio. And you can see here it's this K, which I'll talk about a little bit in a minute, and it's described in your text in here for the gauge. Times the standard deviation of the gauge divided by the upper specification limit minus the lower specification limit. So remember, specification limits are always given as information outside of the process. It's something that the customer puts on the company or on the product or part. So the discussion of K is here, but we're going to use 6. And you can see that corresponds to the number of standard deviations between usual natural tolerance limits of a normal population. And that's very similar to what we were looking at control limits, right? We went 3 standard deviations above the center line, 3 standard deviations below, so we'll use that here. So in the example we just had, you might remember we had a standard deviation of 0.887. Calculated based off of the data that we had available to us. So 6 times 0.887 gives us 5.32. The specifications were given as 60 as the higher and 5 as the lower. And so divided by 55, that's a precision tolerance ratio of 0.097 or 9.7%. So is that good or bad? We know that from the prior example what our total variance is and our percent of that total variance that's attributed to the measuring system versus to the part, and depending on, let's say it's frozen yogurt, was pretty good. But how are we doing in relation to the user specifications? And that's what the precision tolerance ratio does for us. So what we know is good or bad is this table here that is taken from this version of some quality assurance information. So precision tolerance ratio of less than 10%, the measurement system is acceptable. I'm going to guess that's in all cases, but again, we might want to look at that and see, but less than 10% is acceptable. So a very small portion of it. If the precision tolerance ratio is between 10 and 30%, then that says that the measurement system is acceptable depending on the product, the cost, etc. If the measurement system if a precision tolerance ratio is greater than 30%, then the measurement system is not acceptable. And the measurement system could be as a result of the tool itself, which would be the case in the example we just did, or it could be a result of the operator, something happening with the operator. So what this is saying is of our total, if 10% of the range of variability that the customer is willing to adhere to, if the measurement system makes up less than 10% of it, then we're good to go. If it's between 10 and 30% of the variability the customer allows, aka the user specification limits, then it depends on the cost and the product, etc. If that precision tolerance ratio is over 30%, then the measurement system just isn't acceptable to have 30% of the user specification range taken up by variability due to the measurement system, okay? So that's how we determine that. So we have another example, and you can see this is problem 30 out of the 7th edition of the Montgomery text that we're using for class. Let me get to my slide here. So we have data, and you can't see all of the data because I know I'm covering it here, but we have a part number, and we have each part number is measured twice, okay? So 10, 20 times. This actually might be the same as our prior one, I believe. And so the same operator is measuring the parts 20 times. So what can we say about the performance of the new gauge relative to the old one? So we have a new system that we have measured the same 20 parts and come up with these weights, whatever it is, compared to an old gauge system. So what can we say about the new system? And if specifications are 25 plus or minus 15, what is the precision tolerance ratio for this gauge, and comment on the accuracy of that. So here's a little procedure that we would always want to follow, is we would construct the X bar and R charts when we have a single operator. This is the way we would do it. We construct the X bar and R bar charts. We calculate the variance due to the measurement system analysis, and that's what we did in the very first example. And then we calculate the total variance by running all of the part number information, part measurement information in Minitab or Excel and determining what the total variance is. Then we can back into the variance due to the part, because we know variance due to the part plus variance due to the measurement system equals total variance. So we can get variance due to the measurement system from the data. We can get total variance from the data and then back into what is the variance related to the part. Then we'll calculate the precision tolerance ratio and explain the analysis. Okay, so we have the data graphed. So I took this data here and I ran it through Minitab, and I have my range analysis, very similar to the first example we did, and then the sample mean. So again, the range, I see that all the points are within the control limits, so that tells me that the operator isn't having any trouble measuring the part. And I see some parts are out of control on my X bar chart, but again, that's okay because we're not looking at the variability of the mean of the process itself here. We're looking, the control limits are set based on the variability of the same part being measured multiple times. So it's okay that parts are outside the control limits. And like the first short video that you watched, we can see that we have differences in parts, so this is probably a pretty good analysis. So the same way that we did before, we have the R bar from the range chart. We know that the estimate of the standard deviation is R bar divided by D2. We still have the same D2 because we have two individual measurements within each sample. And so R bar divided by D2 gives us the variance of the measurement system, because this is the variance due to the same part being measured twice, so it's the variance due to the measurement system measuring the same part twice. And then when we square the variance, when we square the standard deviation, we get the variance, and so that 2.482 squared gives us a variance due to the gauge itself of 6.16. We use this data set in total, and these slides are posted so you can see the total data set in the slides that are posted. We put this in Excel or Minitab, and we see that the variance of the data set in total is 15.395. So we can back into, again, the variance due to the part by showing that the variance in total we know equals the variance of the part plus the variance of the gauge. We know the variance in total is 15.395 from running the data, minus the variance of the gauge, 6.16, that we got from the R control chart based on the differences in the data. And so the variance due to the part is 9.235. And then calculate the precision tolerance ratio. Sorry, it looks like I'm going to be covering a little bit of it here. The precision tolerance ratio, again, is 6 times, we chose K to be 6, times the standard deviation of the gauge. So we know the standard deviation of the gauge we have right up here that we calculated in the prior chart, divided by the upper specification limit minus the lower specification limit. We see that 25 plus or minus 15 is 40 minus 10, and so that turns out to be 0.496 or 49.6. So if we refer to the table on the prior slide, the precision tolerance ratio of greater than 30% indicates that a new gauge is needed. So this is of the new gauge. So this is telling us that the new gauge is not sufficient because the precision tolerance ratio is greater than 30%, and so it is not going to work out right. But let's go back and answer, okay, well, let's go through these first. And then calculate the PT ratio. Okay, so that's what we just did. So then let's go back and answer the questions of the problems. What can we say about the performance of the old gauge relative to the new one? So if you remember, you can look back in the slides if you have them in front of you. The percentage of the variance, percentage of total variance due to the gauge with the original one, the old one, was only 8%. 8% of the total variance was a result of the gauge. In this new one, we just calculated here the in this new one, we calculate down here the percentage of the total variance that's due to the gauge is 6.16. That's the variance of the gauge. This new gauge is 6.16 divided by 15.395, the total variance. Sorry that I'm covering it. 6.16 divided by 15.395, that's 40%. So here we have 40% of the total variance is due to the new gauge. So if I compare 8% of total variance being due to the old gauge versus 40% of total variance being due to the new gauge, it looks like the new gauge is, I'm sorry, the old gauge. The old gauge is a better tool because it's less of the total variance than the new, okay? And then if we look at the precision tolerance ratio, same thing. The precision tolerance ratio here is 49.6%, which is much higher than what the precision tolerance ratio is with the old gauge, is only 10%. You can calculate this for yourself. If you take the 6 times the standard deviation of the old gauge, go back in the slides and look at that. That was 0.887. 6 times 0.887 is the standard deviation of the old gauge divided by the new limits, 40 minus 10. That gives you 9.7%, a little different than we saw before. I'm sorry, actually, that gives you, if you do it with the new standard, with the new specification limits, that gives you a number of 18%. And we would want to compare the precision tolerance ratio of the gauges against the same user specification limits. So for whatever reason, the specification limits changed. With the updated limits, the new gauge has a precision tolerance ratio of 50%, and the old gauge has a precision tolerance ratio of 18. This is with the old specification limits. To get the 18%, it's 6 times 0.887, which was the variance of the old gauge, divided by 40 minus 10 divided by 30, that's going to be 18%. So 18% is better, a better precision tolerance ratio than 49.6. And if we go back to our table, we can see that while 18 is not less than the 10, depending on what our product is, what the application is, that very well may be acceptable, the old gauge, versus the new gauge is greater than 30%, it's almost 50%, so that is definitely not acceptable. So back to the original question and the problem, both cases, when we look at the variance of the gauge as a percent of total, the old gauge wins. When we look at precision tolerance ratio, the old gauge wins because it has a lower precision tolerance ratio, even with the updated specification limits. And that is the answer to that problem. Now here is a practice problem for you to do, and again this is in the slides that are posted too. So bring the answer, your analysis to class, and we will talk about it in class. Okay, so thanks very much. Next we'll move on to our third video in GaugeR&R and a further some more concepts and another practice problem that has multiple operators instead of just one. Thank you.